Hello everyone, welcome to section 3.1, the beginning of chapter 3. What I'd like to say before we jump into chapter 3 is just kind of the big idea of what we're going to be doing in Math 141, Calculus 1. So I would say that Pre-Calc 1 really has three main sections. The first thing we're going to talk about are polynomials. We're going to learn how to graph polynomials. We're going to learn the behavior of polynomials. That's really the first big hunk of this class. I would say part 2 of this class, what we're going to be doing is kind of a big review of Math 99. We're going to be talking about functions, how to do operations on functions, adding, subtracting, multiplying, dividing, composing functions. We're going to be talking about their domains. We'll be talking about exponential functions, logarithmic equations, exponential equations. And we're going to be talking about piecewise functions. Then, part 3 of this class, we're going to be talking about these things called conic sections. The word conic should remind you of the word cone, and what we'll be doing is we'll be taking slices of a cone to get different graphs. So those are called conic sections. But to begin, let's go ahead and delve into chapter 3 from the beginning on our study of polynomials. So I would say the simplest polynomial that we can talk about is something that's called the quadratic, something we call a degree 2 polynomial. So let's go ahead and write that up. So a quadratic is a degree 2 polynomial. What the word polynomial means, poly means many, and nomial kind of means terms, so it means many terms. And when I mean second degree, what this means is the largest power on the variable is a 2. So let's write a general form of a quadratic. It'll be something of the form ax squared plus bx plus c. So we have something that has many terms. Terms are just things that are separated by addition. And it's a second degree polynomial because the largest power in the variable is a 2. And I should say here that a cannot be 0 here. If a is 0, we wouldn't have this x squared term. It would no longer be a degree 2 polynomial. It'd no longer be quadratic. It'd actually be something of the form bx plus c. This should kind of remind you of like mx plus b, just the variables are different. It'd be the equation of a line, which wouldn't be a quadratic. So really I would say our main goal here, our goal in this section, is we want to graph quadratics. So that's our goal here. Really, in all the sections, we're going to be wanting to graph all different degrees of polynomials, but we'll start with the second degree of the quadratic. Okay, so what I'd like to do is let's start with the most simplest quadratic we can possibly think of. Going back to our toolkit functions, let's think about the function f of x, which is equal to x squared. I hope we know what this graph looks like. The timeless, the classic, the parabola. Looks something like this. You can think about why the graph looks like this. First of all, if I input a positive value, it's going to give me an output of a positive value. It curves because the values are getting bigger. If I plug in 1, I get out 1 squared or 1. But if I plug in 2, I get out 4. If I plug in 3, I get out 9, so it's getting bigger. If I plug in negative values, when I square a negative value, it becomes positive. If I plug in negative 1, I get out positive 1. If I plug in negative 2, I get out positive 4. If I plug in negative 3, I get out positive 9. So any quadratic has this general form. So something I'd like to label on this quadratic here is this spot here, which is at 0, 0. We call this the vertex. The vertex of the parabola. So I might use the word parabola and quadratic. They mean the same thing. And for this specific graph, notice that the vertex here is the minimum value on this function. So this is the simplest thing I can possibly give you. This is what the graph of x squared looks like. But let's do something a little bit different here. What I'd actually like to claim here is that any quadratic, anything that is in this form, is really just a transformation of the simple x squared. Now, if you are uncomfortable with function transformations, this might be a good time to take a look at my function transformation review video, maybe before continuing. Okay, so I'm claiming that I can write any quadratic like this as a transformation of this graph here. So let's do something a little bit different. Let's say for right now, we're just going to draw kind of rough sketches. So as an example, we'll be drawing detailed graphs, and I'll want you to draw detailed graphs in the homework, but for right now, let's just draw loose sketches. So let's draw a rough sketch of the following. So let's say this is f of x, which is equal to, how about x minus 2 squared plus 5. So looking at what I've written here, I hope we can see that this is a transformation of the graph x squared. Notice here I've subtracted 2 directly from the x value. What that does is this shifts x squared to the right by 2 units. And this plus 5 here, since I'm adding 5 to the outside of the function, this is going to shift x squared up by 5 units. So if I take a look at the graph of just x squared and x, that looks something like this. Remember, its vertex here is at the origin. Now, if I want to graph this function f of x, what I've done to this graph is I've shifted right 2 units and up 5 units. So if I want to sketch a graph of f of x, what I'm going to do is I'm really going to be shifting the vertex right 2 units and up 5 units. So 1, 2, and up 5. 1, 2, 3, 4, 5. I have the graph. A rough sketch of the graph f of x here. I've shifted the vertex over 2 units, up 5 units. This is the vertex. Notice the vertex here, if I want to write its coordinates, its vertex is 2 and 5. Let's do another example. Okay, let's try and draw a rough sketch of, let's say, f of x, which is equal to x squared plus 4x plus 1. Now when I look at this graph, or I look at this function here, I'm saddened. This looks like a general quadratic, but I can't see how it's a transformation of x squared. How has it been shifted? I can't visually see, I can't look at this. How has the vertex moved left or right? How has it moved up or down? I don't know how to visualize this. How do I graph it? Where is the vertex? So what I would like to do here, a common thing we do in math, is we try to write things in different forms. What I would like to do is I'd like to take this graph here and I'd like to massage it in a good form. What I would like to do is I would like to do a little bit of massaging, and I wish I could write this function in the form x minus h squared plus k, and maybe I'll put an a out front. If I could write the function in this form, I could clearly see how it's been transformed. I would know how it's been shifted. I would know it's been shifted to the, again, in this case, if h is positive, I'd be shifting to the right by h units. If h was negative, I'd be subtracting a negative value. I'd be shifting it to the left by h units. If k is positive, I'd be shifting the graph up k units. If k was negative, I'd be shifting it down k units. Now this a value, if you go back and think about our function transformation, well, what a is going to be I'm multiplying the outside of the function by a. That's going to stretch the parabola, or it could compress it. So also, if we're thinking about in terms of reflections, I guess let's draw this really quick here. So there could be two values for a. If a is a positive value, what I'm doing is I'm taking my quadratic and I'm stretching it upward, so it'll still have that general shape. So if a is positive, I'm thinking about the function, I don't know, let's draw x squared again over here. Drawing x squared again over here. So in this case here, I would have shifted it right h units. I don't know, maybe let's say this is h. It's not necessarily 3, just some arbitrary value h. I'm assuming it's positive in this case. And maybe I'm moving it up, I don't know, k units. So this is where the vertex would have been shifted. So if I have it in this nice form, I know that its vertex would be at h and k. If a is positive, I've stretched this graph, but I've still kept it in its general shape, which means it would still be pointing upward. It would be a happy face parabola. The graph would look something like this. It would be a happy face parabola, and its vertex would be at the value h and k. That's if a is positive. This is if a is positive. It'd be a happy face parabola. If a is negative, okay, I would still be shifting the graph, I guess if h is positive, right h units. If k is positive, I'd be shifting it up k units. But now if a is negative, I'd be multiplying the outside of the function by a negative value. So all my positives, all my outputs used to be positive, I'd be multiplying by a negative. So now I'm taking those positive values and making them negative. I'd have a reflection over this x-axis, so it wouldn't no longer be happy face parabola, it'd be a frowny face parabola. So this is what it would look like if I had my a value being negative. So this form of a parabola, we call this the vertex form of a parabola. Because if I have it in this form, it's screaming at me where the vertex is. The vertex is at h, k. Now, the book, I don't know, I'll write it in red because I hate what the book does. The book calls this standard form. You know what I think about that? This. Blah. Blah. Standard form. Why does the book call this the standard form? In most textbooks, I hear this called the vertex form. The book calls it the standard form. What I've known the standard form to be of a parabola quadratic ax squared plus bx plus c. For some reason, the book is calling this standard form. So when you hear standard form in the context of our book, think vertex form. I might call this vertex form, but the book says standard form. It's meaning vertex form. Okay, so that's our goal. I want to massage this function to look like that. How am I going to do that? So how are we going to do it? How are we going to massage this function? Okay. Okay, so let's go ahead, I don't know, over here in blue, we have what I'm going to call a vertex form. We want to get this to look like x minus h squared plus k and then an a. This is our goal. Okay. So notice here a piece that I need in this form is I need something of the form x minus h quantity squared. This is a perfect square. So what I'm going to do to this piece is I'm going to complete the square on it to get it into this form. So if you don't remember how to complete the square, make sure to take a look at my video for a review of how to complete the square. Okay, so how are we going to do that? Okay, so what we're going to do here is whenever we complete the square, we always want to complete the square on something of the form x squared plus bx. We want to complete the square we complete the square on something. Let's complete the square on something that looks like this. If you have something like this is what we want to complete the square on. So I have those first two terms here. I have the x different form. The first thing I'm going to do here is I'm going to group these two pieces here in parentheses. So let's write this as x squared plus 4x. I'm going to leave myself a little bit of room here. Plus 1. So what I want to do here is I want to add a number on the x squared plus 4x piece, so this factors into a perfect square. And the number we add here is, remember, we take the coefficient in front of x, we cut it in half and square it. What I'm going to do is I'm going to take this 4, and take the 4, I'm going to cut it in half, and I'm going to square it. So I'm going to be adding 2 squared right here. So we'll do that. We're going to add a 2 squared. Now the reason I like to leave it as a 2 squared, because it's going to, instead of writing a 4, it's going to help remind me how it factors. But I can just go on and adding a 2 squared here because I've changed the value of the function. I've added 4 to it. So I'm going to use the second best trick in the math book. First best trick in the math book is multiplying by 1. The second best trick in the math book is adding 0. So if I've added 2 squared, I have to subtract 2 squared to balance it out. Okay? So now, what I've done is now x squared plus 4x plus 2 squared, that'll now factor to x plus 2 quantity squared plus, what is this, 1 minus 4, that'll be negative 3. Or we could write this as x plus 2 squared minus 3. Yes! I've now taken this quadratic here and I've massaged it into a form where I can clearly see how it's a transformation of the function x squared. If we want to know what the vertex is, notice that I've shifted x squared, I've shifted to the left 2 units, and I've shifted it down 3 units. It kind of looks funky in this form. If this is throwing you off, think about it like this. An x minus, how about a negative 2 squared plus a negative 3. So the h here would now be negative 2, and the k would be negative 3. So the vertex is at negative 2 and negative 3. So I was able to write this function in vertex form. Let's do another example, and then we'll go on to sketching detailed graphs of these. Okay. Okay, as another example, let's say we have the function f of x, which is equal to x squared minus 8x plus 8. So I want to write this in vertex form. So what we're going to do is we're going to complete the square on the first 2 terms here. So we have f of x, which is equal to x squared minus 8x. I'm going to group the first 2 terms. I'm going to leave myself a little bit of room, and I'm going to add 8. So I just really grouped these terms together, these first 2 terms. So now what I want to do is I want to add a number here so this piece factors to a perfect square. So what am I going to add here? Well, I'm going to take this middle coefficient here, so that's a negative 8. I'm going to cut that in half, and I'm going to square it. So that's going to be a negative 4 quantity squared, and that's what I'm going to add. So I'm going to go ahead and add I'll do it in blue, I'm going to add a negative 4 squared, but I can't just add a negative 4 squared. I also need to subtract a negative 4 squared to balance everything out. Okay. So you could write this as a 16, but the reason I like to leave it as a negative 4 squared is it's going to remind me how it factors. F of x is going to be equal to, this will now factor to x minus 4 squared plus, what do we have here? This is going to be 8 minus, 16. So this will be f of x is equal to x minus 4 quantity squared. This will now be minus 16. Or, if you'd like, f of x, x minus 4 squared, plus a negative 16. So this is exactly in that vertex form. So what I've done is I've taken the function x squared, I've shifted to the right 4 units and down, oh this is 8, sorry, minus 8. And I've shifted it down 8 units. So here, the vertex is at 4 and negative 8. Okay. Let's do another example. Let's say I have the function f of x, which is equal to 5x squared plus 30x plus 4. Now this is an example where the coefficient in front of x squared is not 1. So what are we going to do in this type of situation? I'm still going to group the first two terms together. Also, I forgot to say this, but anytime I start a new example, I forget to say it, you should always pause the video and try it on your own first. So I'm assuming you did that. Okay. So let's go ahead and group the very first two terms together. Okay. So I have f of x is equal to, let's leave it like this for now. Remember when we complete the square, we want it to be on something of the form x squared plus bx. So when I complete the square, I want the coefficient in front of x squared to be 1. Over here it's 5. So what I'm going to do is when a situation happens where the coefficient in front of x squared is not 1, I need to factor out a 5 from the first two terms here. So if I go ahead and do that, I'll factor out a 5. And what I'm going to be left with is x squared plus 6x in the parentheses. I'm going to leave myself a little bit of room here. Adding 4. So now what I'm going to do is I'm going to complete the square on this piece. So I'll look at this term 6. I'm going to take 6, I'm going to cut it in half, and I'm going to square that. So I'll get out 3 squared. So I'm going to go ahead and add 3 squared inside the parentheses. Now a very common mistake I see a lot of students make is they think that since they've added a 3 squared, we have to subtract a 3 squared here. But we have to be careful. I didn't just add 3 squared to this function. If we think about this 5 distributing, what I've actually added is 5 times 3 squared. So what I need to do here is I need to subtract 5 times 3 squared to make sure I've added 0. Beautiful. Okay. So let's factor this. So here we have f of x will be equal to a 5. Okay. This will factor to a x plus 3 squared. Okay, what do we have right here? This is a plus a 4 minus, what is that, 9 times 5. 9 times 5 is 45. So I have a 5 times an x plus 3 squared. 5 minus, so what is that? That's going to be, what, negative 41. Okay, so beautiful. I was able to massage this function here so I could see it as a transformation of x squared. I can see here the function x squared has been vertically stretched by a factor of 5. It's been shifted to the left 3 units and down 41 units. So in this form, I can instantly read where the vertex is. The vertex has got to be at negative 3 and negative 41. Okay, let's do one more example. About sometimes when the numbers aren't so nice to us. Okay, so let's say I have f of x is equal to negative 2x squared plus 10x. How about plus? Okay. So go ahead and pause the video and try this on your own. Okay, so we're going to group the very first two terms together. So I have f of x. So since the coefficient in front of x squared is not 1, I need to actually factor out the negative 2. So let's go ahead and factor out this -2. So if I factor out the -2, I'll be left with an x squared, let's say minus 5x. I had to factor a negative out of this. Notice if I distribute back in the -2, I'll get -2x squared, and I'll get -2 times -5. I'll get back to my 10x plus 5. Just leave myself a little bit of room here. Plus 5. Okay. So now what I want to do here, the number I want to add is what I want to do is I want to take this -5, I want to cut it in half, and I want to square it. And I'm going to leave it just like this. So what I'll add is I'm going to add a -5 squared, -5 squared inside the parentheses. But since I've added a -5 squared inside the parentheses, what I've really added is a -2 times a -5 squared. So I need to subtract a -2 times a -5 squared. A lot of negatives going on there. Okay, so let's clean this up. So we'll have that f of x is equal to -2. See, this is going to factor to x minus 5/2 quantity squared. Let's see what we have over here. We'll have a plus a 5. Notice I have two negatives here, so I'm going to get a plus. I'm subtracting a negative. So I'm going to get plus a 2. -5/2 squared, I can distribute the square to each piece. So -5 squared is 25. 2 squared is 4. So I have a -2 times x minus 5/2 squared plus, what do I have here? I have a 5 plus, how about we write that as 50 over 4? Or how about we see it like this? How about we see that there's a 4 here and a 2 here. The 2 will cancel with one of the 2's and the 4, so this will be plus 25/2. So let's just, so I don't have to keep rewriting this, let's just focus on this piece right here. I want to add this together. So I'll do the first best trick in the math book. I'm going to multiply the 5 cleverly by 1. So 5, so it's 5 over 1. I'm going to multiply that by 2 over 2. I guess I have this 5 over 1. I'm going to multiply that by 2 over 2 plus this 25/2. So I now have a common denominator of 2. So I'll have 10 plus 25. I'm going to get 35/2. So this is going to be a -2 times an x minus 5/2 quantity squared plus a 35/2. And there we have it. This is the vertex form of this quadratic. So now what's great is I can clearly see how this function has been transformed from x squared. Notice the negative, its function is frowny face. It's taken x squared and it's reflected it over the x-axis. I've shifted it to the right by 5/2 units, and I've shifted it up 35/2 units. So here its vertex is at 5/2 and 35/2. I hope you found this helpful, and the next video we'll be drawing detailed sketches of these graphs. We'll see you then.